Well, thanks everyone for coming back. Oh, do we need to switch the slides? Oh, there you go. Okay, great. So we're going to dive a little bit deeper into some of the math that we're previewing with Qubit Touchdown. And so just to start off, I'm going to be drawing almost entirely from my textbook. So basically, this textbook is my lecture notes and all the homework problems that I do in my class. So this book is literally my class at Creighton. And so the way that I teach it is we actually spend a good amount of the class, about a third of the class, on classical computing. Because a lot of times people will talk about, oh, like qubit is a quantum version of a bit, or like a quantum gate is a quantum version of a logic gate. But my students don't know what a bit is, or haven't really thought about it deeply, or what a logic gate is. And in a lot of the things that we do in quantum computing, they're done because there's a whole history of how we do things in classical computing. And so we spend a good amount of time talking about classical computing, and in particular the aspects that are going to translate over to quantum. And when I ask students in course evaluations at the end of the semester about whether or not that time was valuable or whether it was like wasted, where they would have rather done more quantum, the feedback is overwhelmingly positive that we should keep this classical part. Another thing is, a lot of my students, are not going to go into quantum computing as a career unless they're like one of my research students and then they go to, they're in grad school currently. And so for a general student, like them learning more classical computing and how computers work is probably going to be more useful to them in their careers. So for those who pivot into other areas of STEM from their physics major. And so I think that there are broader reasons for my particular audience for why that is. After that, we play Qubit Touchdown as the start of this chapter on one quantum bit, and then we'll be unpacking that now. And then you see that linear algebra isn't talked about until after we've done a whole chapter on one quantum bit. And the idea is that linear algebra is going to emerge as a tool to make everything easier. So we do everything with elementary algebra, and it starts to get tedious, and it's like, hey, wouldn't it be nice if there's another way? Here's another way. So yeah, linear algebra emerges as a tool versus them having to know it, because I mentioned, I think, that students don't have to have linear algebra to take my course. Then we go into multiple quantum bits. The new quantum programming using IBM's QIST. This chapter is now out of date because QIST went to version 1 last year, and all of the old code that's before version 1 no longer works. So I need to update this. So, and then talk about quantum entanglement, quantum protocol. So we'll do one together on quantum teleportation. Then quantum algorithms, and the next steps is what came up in terms of like what are some jobs in quantum, what are some things for future reading, some points where it's like, we kind of presented things where like this is how things are, like a qubit is a point on the Bloch sphere, but in actuality, there's states where you can be inside the Bloch sphere. Basically I point out things where it's like if you go deeper, you'll realize that some of the things we talked about, we purposely limited our scope. So things like that. All right, so one of the ways that I like to start off people's understanding of quantum computing, besides Qubit Touchdown, is with a sports analogy. So I guess we're all doing all sports. So this is not, actually this is going to be football, but it's going to be international football, so soccer. So in soccer, right, it's football because you typically can't use your hands, you use your feet. Because of that, soccer looks a certain way. But imagine you change the rules where now all the players can use their hands. And so that's going to look really different, right? And in some cases, it's faster to like swat the ball out of the air or grab it and run with it. But not everything is faster. If you want to get the ball down the field as quickly as possible, it's probably still fastest to kick it. And so this is what we're doing with quantum computing. We're changing the rules of the computer, so now it can use its hands, so to speak. And because of that, it can do certain things faster than a normal computer can, but not everything is necessarily faster. And so I like this analogy for a couple reasons. One is because a lot of pop articles about quantum computing make it sound like a quantum computer is just like a massively parallel classical computer that can solve all of our problems. And this makes it clear that, no, there are limitations to quantum computers, just as there are limitations to classical computers, that they follow a certain set of rules or laws, and Because of that, yeah, there might be some things you can do faster with a quantum computer, but that doesn't mean everything is faster. And so I like this, again, because it just immediately dispels this misunderstanding that a lot of people have in thinking that quantum computers can just do everything faster. All right. In the chapter on classical computing, we go into complexity classes. And so obviously in a whole semester you can go much more slowly. But just to kind of give you a quick primer on it, you can think of these different terms like P-space, NP-complete, NP, BQPP as being the class of problems that different types of computers would be able to solve. So our currently existing computers, they can solve the problems in this class P very quickly. So the types of problems it can solve quickly are if a graph is connected, if a number is prime, it can solve matchmaking efficiently. And so again, these are problems that are easy for our computers. And then beyond that, it's not known if our current computers can solve those problems. So in the course, when you have a lot more time, a third of the course talk about classical computing, you can get into this more. And again, I think students don't realize that classical and quantum computers have limits. And this is kind of them coming to grips and understanding, hey, our current computers have limits as well. Sometimes they think, oh, if you just build a bigger supercomputer, you can solve this. But actually it's like, no, because the scaling is such that you wouldn't be able to build a classical supercomputer big enough. And so, yeah, so I want to focus on P. So these are things that a normal computer can solve quickly. BQP are the things that a quantum computer can solve quickly. And you can see that everything that a normal computer can solve quickly, a quantum computer can also solve, but it can solve things beyond that. And the big example is factoring. So many of you might have heard about this. So one of the reasons why people are interested in quantum computers is because they can factor efficiently. And that would break that would basically break our currently used encryption schemes. And so, thankfully, NIST has been working on this for 8-9 years. There's now new cryptography standards that are going to be safe from attacks from quantum computers. And so the world is now working on transitioning to those cryptography algorithms. So those are all standardized now and are out there. But the old ones, like RSA, those would be broken by quantum computers. Yeah.
But there is post-quantum crypto at the moment.
Yeah, so I'm talking about post-quantum. Yeah, so basically these are the new algorithms that are safe from attacks from quantum computers, as far as we know. We don't know actually that factoring. We don't actually know that a normal computer can't factor quickly. It's just that we've worked so hard on it over half a century, and it's like it seems really, really hard, so it's considered safe. But anyways, so the idea here is that quantum computers can do more than classical computers can, but it can't do like every single known problem. So all of these problems out here, like n by n chess or Go, like you can't just solve it with a quantum computer. So yeah, so these two slides are just to kind of level set that quantum computers are exciting. There's cool things that they can do that our normal computers can't, but it's not a solution to everything. All right, now let's get back into quantum bits. So we talked about the block sphere, and the north pole is 0 and the south pole is 1. And we can look at different states that are on other places on this sphere. So here's a point on the equator on the positive x-axis, and remember we call that state plus. So this state is actually 1 over the square root of 2 times 0 plus 1 over the square root of 2 times 1. So it's equal parts 0 and 1. That's why it's on the equator. And so what are some things that are like equal parts, like half-half? Well, sorry, this is what we abbreviate as a plus state. Well, you can think of a spinning coin in some sense as being half heads and half tails. And so while it's spinning, you don't know what it is yet, but it's has 50-50 chance of being heads or tails. And once you measure it, you'll get either heads or tails with a 50-50 chance. And so you can think of this quantum bit as being similar, where on the equator, it's halfway between the north and south poles. And so it's half north pole, half south pole. But once you measure it, you get the north pole with a 50% chance and the south pole with a 50% chance. So how do you get the numbers 50-50 or half and half from this state? Well, if you take the square of the coefficients or particularly the norm square, because we're going to allow complex numbers in a moment. You can see that if we take the norm square of this coefficient, we get a half. And if we take the norm square of the other coefficient, we get the other half. And so this is indicating some things. So first thing we've already seen, qubit is quantum bit. Superposition is what we call a combination of 0 and 1. I think it was on my qubit touchdown slide. I don't know if I said it. These numbers in front, these coefficients, they're called amplitudes in quantum computing. And if you square the amplitude, you get the probability of that particular outcome. So with a 50% chance you'll get 0, 50% chance you'll get 1. And once you actually get your 0 or 1, it is now exactly 0 or exactly 1. It's no longer a mixture of half-half. Just like your coin, once you smack it and it's heads, it's no longer half heads, half tails. It is just heads. And so in quantum mechanics lingo, we say that the qubit collapses to 0 or 1, so it just becomes one or the other. And then one thing that you'll point out is that the total probability has to equal 1. So we see that the state is normalized. Okay, let's look at some more examples. So here's another qubit where the state is here on the equator. So we've shifted over from the x-axis by 30 degrees, by pi over 6 radians. So this state is actually written like this. So it's 1 over root 2 times 0 plus e to the I pi over 6, so that's my 30 degrees, or pi over 6 radians, over the square root of 2. And this is on the equator. So again, if we measure this, it should be a 50-50 chance of getting 0 or 1, the north pole or the south pole. And if you take the norm square of those amplitudes, again, you get a half and a half. Here's another example over here on the y-axis. So now we've rotated by an angle of 90 degrees, or pi over 2 radians. E to the I pi over 2 is just I. So this is written as 1 over root 2, 0 plus I over root 2. And that's what we were calling the state I earlier. And again, if you measure this, you should get a 50-50 chance of getting the north pole and the south pole. What about a state that's not on the equator? So this one is now 30 degrees rotated up from the x-axis. So this state is this. It's root 3 over 2, 0 plus 1 half 1. Before you take the norm square of these, just intuitively, if you were to measure this, are you more likely to get the north pole or the south pole? North pole, because it's closer to the north pole. And if you take the norm squares, you get a 75% chance of getting the north pole and a 25% chance of getting the south pole. And so I like this geometric way of representing a qubit because I feel like students can gain a lot of intuition quickly without getting as bogged down by the math. And here's another example. So this one's like behind in the back, like in the southern hemisphere. This state looks like this, 2/3 0 plus 1 minus 2i over 3 times 1. If you find the probability, so about this one, I said it's in the southern hemisphere, are more likely to get 0 or 1? 1, you're more likely to get the south pole. The probability that you get 0 is the norm square of that, which is 4/9, which means that the other probability must be what? 5/9, so that it adds up to 1. So, with my students, I do spend a good amount of a class reviewing complex numbers. That's always challenging because you have the students that are just like really strong at math that are like, this is so boring, I know complex numbers. And you get the students that are like, I really need this review. So, okay. Yeah.
I've actually, because I picked your book for my class, but I read Chris Bernhardt, and he doesn't do the complex numbers. And I know complex numbers, but my students probably don't, so I'm trying to get away with it. But I think I would still give them E's for intuition. But I would just tell them I is the square root of -1, right? And
yeah.
They don't really need to know the phase and the the geometry behind it. But I have a question about the previous example.
And the previous slide?
The one on the right.
Yeah. So this is e to the I pi over 2.
This math e to the I, and you said
Pi over 6.
Pi over 2.
Oh yeah.
When you get a 1. So
yeah.
That's like some math concept.
Yeah, that's from Euler's formula. So in the textbook, we review what Euler's formula is, how to go from complex numbers in the exponential, like polar form, to like Cartesian form. We do all that.
Yes.
How to take the norm square of a complex number, so you multiply it by its conjugate. So we do all that in the book because that's what I do in my class.
I did read that, but
You can actually, like most, basically everything else I'm going to do after this like doesn't actually use the complex numbers, and most quantum algorithms don't use it. It's really not till you get to an algorithm very close to the end of the textbook on phase estimation and shores where you need complex numbers.
Before you
Yeah.
could might go because it's just a phase.
Yeah.
But here, so I could just tell them e to the I pi over 2 is 1, or is I.
Mhm.
And I just give that to them as a formula, and then I can skip that.
Yeah.
But my real question here was how it switched. So this is pi over 6?
Yeah, because this is pi over 6 radians rotated away from the x-axis. And then this one's rotated pi over 2 radians away from the x-axis, or 90 degrees.
Pi over 2, 90 degrees. Oh, pi over 6. Okay, and it is around the x-axis.
Yeah, so from the x-axis, you're rotating 90 degrees along the equator.
Yeah, along the equator,
Yeah.
that's what that is. Yeah, so go this way, and that's just the same one, but the smaller angle. That's like...
Yeah, this is an angle of 30 degrees. Yeah, because 30 degrees is pi over 6 radians, and then 90 degrees is pi over 2 radians.
Yeah, so
I say the prerequisite for this course is pre-calculus, because I assume they know radians and have seen the unit circle. But yeah.
Are both amplitudes allowed to take complex values?
Yes. But you can always, I mean, I'm not talking about this here. I do in my class because we have a whole semester. You can pull out a global phase, so you can always make the amplitude of the 0 to be real. Yeah.
Can you do this class without complex numbers?
Everything except the last two algorithms, so basically phase estimation and shores, right? But everything else, yeah. So this is actually a choice for me because like I intend this course to be intro to quantum for STEM majors. So even though they haven't taken the math yet, they will learn the math, they will go into science. And so the idea is I'm okay with pushing them a little bit more with the math. And certainly if they go to grad school, if they want to do research with me, complex numbers will come up. So I think depending on the goals, and I know, for example, like Scott Aronson at UT, like he teaches intro quantum without complex numbers, and I can see that working depending on the audience. So, yeah. Yeah, I do this because this is literally my class and how I teach it to my students and what fits them. So, yeah, there's definitely a lot of room for changing things up for different audiences.
My point here was just, this was confusing, but if you actually still had it written out as e to the IP over 2, then it would be easy to see a 30 degrees versus
Yeah.
90 degrees.
I think the book probably shows that, and I just did it in the slide.
Well, I'm not critiquing, I'm
Yeah.
just learning so I can
Yeah.
pass the
So one thing is like we do this to just help to understand the intuition of like measurement, that northern hemisphere, southern hemisphere, equator, things like that. And then, you know, after a whole class of things like this, then and reviewing complex numbers, then we get into, okay, given a particular state, how do you actually show where it is on the block sphere? So how do you calculate the angles that this one is actually 30 degrees, this one is 90 degrees, things like that. So then we review like polar coordinates and things like that. So yeah.
Polar coordinates, I was going to say for spherical coordinates, but
Sorry, spherical. Yeah.
Would it be right to say the coefficient on 0 is just a trig function of phi, and the other coefficient is e to the I or e to the I theta in spherical.
Yeah, so this is actually cosine of phi over 2 and sine of phi over 2, and then e to the I theta.
Okay.
And you can flip theta and phi depending on what convention, if you're a physicist or a mathematician. Yeah.
So if I remember correctly, the amplitude, absolute value squared actually tells you the z coordinate, right? Like where if you normalize it, so 1.
Yeah, basically if you were to like, basically
1, 0.
this one, if you project it over to like the z-axis, yeah.
Well, you have to have
Right.
the probability goes from 0 to 1, where
Yeah,
0.
you have to
so
Yeah, you have to,
Scale.
yeah, you have to,
project it onto the z-axis
and then
normalize
Rescale it,
yeah.
so 0 would be 1, and 1 would be 0.
Yeah, there's a lot that I'm not going to talk about today, given that we have 4 hours instead of like 40 hours for a class. including like inner products and like projections and stuff like that. So, yeah. But the idea is like this is linear algebra, so you should be seeing these connections if you have that understanding, right, or that background. Okay. Quantum gates. So we already saw quantum gates are rotation. So like the x gate is rotation by 180. So if you start off at 0 and you rotate around the x-axis by 180, where do you end up? Yeah, at the south pole at 1 down there, which is 1. And similarly, 1 goes to 0. Maybe I should mention this. In terms of which way you rotate, it doesn't matter for 180, but for 90 degrees it matters. You use a right-hand rule. So you take your right hand and you grab the axis of rotation. So the x-axis is coming out of the page. So I would grab it like that. And you see how my fingers rotate counterclockwise? So it rotates counterclockwise. All right, so the x gate turns 0 into 1 and 1 into 0. So this is your NOT gate, if you're familiar with logic gates. So an x gate is just a NOT gate. Let's look at another example. A z gate rotates around the z-axis by 180 degrees. So let's look at the plus state here on the x-axis. So if we rotate this around the z-axis by 180 degrees, where does it end up? Yeah, so it ends up on the back there, on the negative x-axis. So again, you grab the z-axis like that because it points up, so my thumb is up, and it rotates around like that to get to the back. And that state is what we're calling, is what we've been calling minus. So that's 1 over root 2, 0 minus 1 over root 2, 1. So this would be a phase of e to the I pi, which is minus 1. And so z turns plus into minus and minus into plus. Or another way of interpreting it is if you compare plus and minus, you see what changed was that the amplitude of 1 got flipped, and then the amplitude of 0, nothing happened. So what the z gate does is it does nothing to 0, but it turns 1 into negative 1. Another gate we saw was the Hadamard gate, one of the gates you can use to score a touchdown. This rotates around the x plus z axis. So this is the axis that is 45 degrees, like between x and z. So it's a little hard. This is the hardest one to see, and my LaTeX drawing skills are not the greatest. Yeah, it's coming like up and out of the page. So again, it's 45 degrees up from x, which is also 45 degrees down from z, like between them. Yes, in the xz plane. So if you're at 0, where do you end up if you rotate around that axis by 180 degrees? This is the hardest one. I literally drew this on a ball for a student with like a dry erase marker, like in office hours, because the student wasn't seeing it. Equator. Yeah, you end up on the equator. So you basically do circles like that. It's not a circle, but you know what I mean, like that. Yeah. And similarly, if you started off at 1 in the southern hemisphere, where do you end up? You end up in the back at the minus state. So what we see is that h turns 0 into plus, and it turns 1 into minus. Okay. And actually vice versa. It will take plus back to 0 and minus back to 1. Oh, this is worth pointing out, actually. If you look at the board game, the actual board, the Cupid Touchdown board, so you see that h will go from 0 to plus to score a touchdown, and you'll go from 1 to minus to score a touchdown. So in the game, you wouldn't ever go from plus back to 0 or minus back to 1. You would just like roll the like die to kick off. But technically, you could go backwards. And if you look closely at the board, there's some faint green lines with some faint green labels. So those are actually also allowed transitions for a qubit, but they don't come up in the game because you would just kick off after you score a touchdown. So those are like hidden in the background. So someone like mowed it into the grass or something. All right. All right, for 2 qubits, instead of having 2 coefficients or 2 amplitudes, we're now going to have 4 amplitudes in general, because you can mean some combination of 0, 0 0, 1, 1, 0, and 1, 1. In my class, we also review binary numbers because I can't assume students know that. Again, if your students have a stronger background, you can skip all that. So now there's 4 different possible measurement outcomes. If you measure your 2 qubits, you can find they're both 0. You can find that they're 0 and 1, 1 and 0, or 1, 1. And what do you think the probability is of getting both zeros? Yeah, 1/16. You take the norm square of that. What's the probability of getting 0, 1? A fourth. The next one? Half. And the next one? 3/16. Does that add up to 1? It should if I normalize my state right. But you see that it just translates over, right? So you just take the norm squared of the amplitudes now in order to find your probabilities. Now let's look at a 2-qubit gate. So this is called a control NOT or C NOT gate. So what this does is if the first qubit is 1, then it flips the second qubit. Otherwise, it does nothing. So it does a flip or a NOT conditioned on the first qubit. So if you look here, the left qubit is 0, so nothing happens to the right qubit, so it stays 0, 0. Left qubit is 0, so nothing happens to the right qubit, so it stays 0, 1. Left qubit is 1, so we're going to flip the right qubit. So this goes from a 0 to a 1, so it becomes 1, 1. And again, the left qubit is 1, so we're going to flip the right qubit, so it becomes 1, 0. So this is a C NOT gate. There's other quantum gates, but these are the ones that we're going to be revisiting. So we could have even more qubits. Let's say we have 3 qubits. How many amplitudes, how many coefficients could there be now? 8. So here's an example of one. Hopefully I normalize this correctly. And the probabilities are just norm square of all of these. Again, hopefully that's right. And in general, if you have n qubits, how many coefficients are there? 2 to the n. So it grows exponentially. So yeah, there's some exponential number of coefficients. I'm just calling this coefficients alpha. And there's potentially 2 to the n of them. All right, and this is an argument for why people think classical computers are less powerful than quantum computers, because if you wanted to simulate a quantum computer in this most obvious way, you might have to keep track of an exponential number of amplitudes. And so as the number of qubits grows, the classical resources you need could grow exponentially. It's not a proof because it might be that there's some more clever way to simulate what's going on with your quantum computer, but certainly it's an argument or some intuition for it. So yeah, there's an exponential number of amplitudes to keep track of. All right, how are we doing on time? Okay, let's keep going. We've got about 15 minutes. Okay, let's dive into a little bit of linear algebra. So I didn't cover any linear algebra last year when I did my intro, and then several of the other speakers used linear algebra. I was like, oops, I probably should have talked about that. So we're going to do a little bit. And I'm going to present this in a way where it might be more suitable for students who have not taken linear algebra yet or who are a little math nervous, let's say. So we just saw this quantum state with 3 qubits. So 1 over 6 times 0, 0, 0 plus 1 over 3 root 2 times 0, 0, 1. Oh, another thing is I lecture on the board entirely, so we're writing this out. And students are copying this down. And they're like, this is getting really annoying. So it's like, we understand that these amplitudes correspond to 0, 0, 0, 0, 0, 1, 0, 1, 0. I should mention that in the first chapter on classical computing, I teach them how to count in binary. So they, at this point, they know how to do this. So it's like, if we understand that these amplitudes correspond to all zeros, 0, 0, 1, and so forth, we don't need to write down 0, 0, 0, 0, 0, 1, 0, 1, 0, and so forth. All we care about are these coefficients. So why don't we just list all the coefficients like that, just in a little table. And so, of course, for this audience, you understand that this is a vector, right? So the idea is we're coming about this as a way of making life easier. So what this implies, and the way I do it with my class is more gentle, you guys are more advanced, is that means that 0, 0, 0 must be the basis vector 1 with all zeros. That way, if you have 1, 6 times this, you get 1, 6 in the top entry. The next one, 0, 0, 1, must be the next basis vector with a 1 there. That way, 1 over 3 root 2 times that is going to give you a 1 over 3 root 2 in the second entry. The next one must have a 1 there. That way, you get a 1 over root 6 in the third entry, and so forth. And so you can go through and do this. And you can generalize this to however many qubits you want, even just a single qubit. Instead of writing root 3 over 2 times 0 plus 1 half times 1, you can just drop the 0 and the 1 and write this as a stack of numbers. What numbers go in that stack? Yeah, root 3 over 2 and 1 half, so just your coefficients. And that makes things much faster to write down. In this case now, the basis is 0 is going to be this vector 1, 0, so that we get root 3 over 2 times that 1 gives you root 3 over 2 at the top, and 1 half there is going to give you 1 half at the bottom. Okay, so we saw that with 1 qubit, you have these basis vectors. How do you go from these to constructing, for example, this basis vector that we had before that was 0, 1, 0? Well, this 0, 1, 0 is actually can be obtained by multiplying these together a certain way. And so this is called the tensor product or Kronecker product. So what we're doing is you're multiplying 0, 1, and 0 using this tensor product. It's implied, but if you want to write it out, we write that multiplication as a times with a circle. So it's like a circle times. And so this is going to be 0 is 1, 0. Tensor 1 is 0, 1. Tensor 0 is 1, 0. And the way that you do this Kronecker product is, if we just focus on these two right now, is you take this 0 and you multiply it by 1, 0. And you take this 1 and you multiply it by 1, 0. So it looks like this. So again, you have 0 times 1, 0, and 1 times 1, 0. So this is going to grow now into a vector of length 4. And so what you get is 0, 0, 1, 0. So 0, 0, 1, 0. And we can do that again now. So you have 1 times this vector, and then 0 times this vector. That's going to give us this giant thing. And if you multiply that out, you get this vector with 8 elements now, with a 1 at the third entry. And this is precisely 0, 1, 0. So this Kronecker product, or tensor product, is the product that you use to go from single qubits to assemble them into multiple qubits. We can also look at quantum gates in linear algebra. So for example, the Hadamard gate, we saw that it goes from 0 to this plus state, which is equal parts 0 and 1 with real coefficients. And we can write that as 1 over root 2 and 1 over root 2 if you want to stop writing this 0 and 1. Oh, I should mention, this notation is called a ket. So this is a ket 0, ket 1. And then it turns 1 into this minus state, which we could write as a vector as 1 over root 2 and minus 1 over root 2. So really, this Hadamard gate, what we care about is what it does to 0 and 1. So it turns 0 into this vector, and it turns 1 into this vector. So we can completely describe H just by listing these two vectors, and we'll do that here. So H gives us this vector if it acts on 0, and it gives us this vector if it acts on 1. And so this is a shorthand now for writing what this Hadamard gate does. And of course, and we can also factor out 1 over root 2 if we wanted. And so of course, to this audience, you guys will know that this is a matrix. And so now we're introducing matrices to students. And one of the things that, when we get to inner products and stuff like that later in the class, I'm not going to do that here. So I'm telling you, a quantum gate can't just be any arbitrary matrix. It has to be a unitary matrix. And those are the ones that make it so that your total probability stays equal to 1. And a unitary matrix is a matrix where it's the conjugate transpose of the matrix is its inverse. Yeah, and I'm not showing you that here. I'm just telling you. All right. So from what we have so far, we can then introduce students to matrix vector multiplication. So we have the Hadamard gate, which is this matrix. It's just a table of numbers. And we know that when the Hadamard gate acts on 0, we get this state, and when it acts on 1, we get this minus state. So let's go ahead and plug in the matrix and the vectors for each of these. So H is going to be this matrix. The ket 0 is going to be this basis state 0, 1, and this plus state is the state 1 over root 2 and 1 over root 2. Similarly, over here, if we plug in, H is, again, this matrix. The ket 1 is 0, 1, and then this minus state looks like that as a vector. So how should we multiply a matrix and a vector so that it equals this? And similarly, how do we multiply this matrix and this vector to equal that? Well, what we can do is we can take the elements of this row and we can multiply it piecewise with the elements of this row. So we do 1 over root 2 times 1 plus 1 over root 2 times 0. And that will give us this top entry. And similarly for the bottom row, we'll do the same thing. We'll take 1 over root 2 times 1 plus a negative 1 over root 2 times 0. So I've written that out here. And you can see now, if I simplify this, we get precisely, or we do the same thing over here, we get precisely 1 over root 2 and 1 over root 2, which matches. And over here, we get 1 over root 2 and minus 1 over root 2, which matches there. And so we can see that the correct way to multiply a matrix and a vector is to do it component by component for each row. Oops, looks like that didn't make the transition. We can also do this using superposition. So we can ask, how does the Hadamard gate act on this superposition, which is the one that was in the northern hemisphere, 30 degrees above the x-axis. So if you want to do this using matrices and vectors, you can just take H as this matrix. This state is this vector. And you can multiply it the way we just said. So you do 1 over root 2 times root 3 over 2 plus 1 over root 2 times 1/2 for the first row, and then similarly for the second row. Then you simplify, you get that. You simplify some more, you get that. And that's equivalent to this state. And so we're not doing any of this here. But when we do linear algebra in my class, one of the things we introduce a bunch is that you can use a computer to do linear algebra now. So we use Mathematica. The textbook has both Mathematica and Sage, because Mathematica is something you have to pay for if your university doesn't have a subscription, whereas Sage is open source and free. So there's both options. And basically, like, all this stuff that you had to do before the long way by hand, you can now just have your computer do it for you. And that makes everything easier. So, all right. So let's look at a little bit more about quantum gates. So the C0 gate we saw was this. So the C0 gate as a matrix should be a 4 by 4 matrix. For the first entry, this is the vector corresponding to 0, 0. For the second column, this is the vector corresponding to 0, 1. For the third column, that's what corresponds to 1, 1. And then this last column corresponds to 1, 0. So again, we're just listing out the results of C0 when it acts on each of the basis states. And one final note is that you can combine quantum gates by using the tensor product or Kronecker product. So for example, if you have 2 qubits that are in the state 0, 0, then this means you're applying the Hadamard gate to the left qubit and the X gate to the right qubit. So the left qubit is going to, H is going to turn that 0 into a plus, and then X is a NOT gate. It's going to turn the right 0 into a 1. So just like you can take tensor products of vectors in order to construct bigger ones, you can take tensor products of matrices as well. And given our time, that's all I wanted to talk about for that. How are we here? It's almost 11. Should we break here? Or?
Up to you when you finish the those are more guidelines.
Good to know, Justin.
Who wants a break now? Raise your hand. Why don't we just do a 5-minute break instead of a 10-minute break? Let's just do a quick 5-minute break. Because I don't know the reasons why someone needs a break, and maybe they really need a break. So let's just take a 5-minute break. Yeah, it's not just number of people. Maybe it's like a real emergency.
Can you go go back. I lost my train of thought.
If we can reconvene so we can get lunch ready.
I still have a lot to cover, actually.
Yeah. If we can quiet it down again and get this going again. Thank you.
All right. So let's talk about entanglement. You don't need to know what this is yet. I'm going to tell you. So let's say we have two qubits in this state here. So 1/4, 0, 0, plus a half, 0, 1, plus 1 over root 2, 1, 0, plus root 3 over 4, 1, 1. And say instead of measuring both qubits, which would give you, 0, 0 is probability a 16th, 0, 1 is probability a quarter, and so forth, we're only going to measure the left qubit. So if you measure just the left qubit, it's either going to be 0 or 1 with some probability. And it's going to be 0 from these two states where the left qubit is 0. And it's going to be 1 from these two states over here. So the probability that it's 0 is going to be the sum of these two probabilities. So it's going to be a 16th plus a quarter, which is 5/16. And then the state is going to collapse so that the left qubit is, so it's going to collapse to these two here where the left qubit is 0. But this isn't normalized now. The total probabilities here is not 1, so we're going to multiply it by a constant to properly normalize it, so it should look like that. And now I can factor out that the left qubit is 0, and the right qubit is 1 over root 5 times 0 plus 2 over root 5 times 1. Okay, so that's one possibility when you measure the left qubit. It could be 0, and then the right qubit, you don't know what it is yet because you haven't measured it. The other possibility is that the left qubit could be 1, which would come from those two states there. So that probability is going to be given by the sum of the norm squares of those amplitudes, which is 11/16, because that total probability should be 1. The state's going to collapse to these two, but we need to normalize it, which gives us this. And now I can factor out that the left qubit is 1. And then the right qubit is this. You don't know what it is because you haven't measured it yet. So what you see here is that if the left qubit is 0, the right qubit is this state. But if the left qubit was 1, the right qubit is this other state. So you see how the state for the right qubit is not the same as this state? So depending on what outcome you got for the left qubit, the right qubit is going to be affected. And so this is what we call entanglement. So the outcomes of the qubits are intertwined in some way. They are entangled together. So the outcome of the left qubit affects the state of the right qubit. It mattered if the left qubit was 0 or 1. Let's compare that to this state of two qubits. We're going to do the exact same thing. We'll measure the left qubit only. If it's 0, the probability is going to come from those two, which is a quarter. It collapses to these two states, which we then have to normalize to that. And we can factor out that the left qubit was 0, and the right qubit could either be 0 or 1 with the 50-50 chance. We don't know. I haven't measured it. The left qubit could be 1 instead. That probability should be 3/4. It collapses to those two states, which we normalize. And we factor out that the left qubit was 1. So now what we see is that whether the left qubit was 0 or 1 has no bearing on the right qubit, because the right qubit is the exact same state in both cases. So in this case, measuring the left qubit doesn't affect the right qubit. And so these are not entangled. So entanglement is just when measuring one qubit affects the other because they are like intertwined in a way. Yeah.
I would think the opposite. The logical reasoning, because so if they're entangled, right? If the first qubit is 0, it's going to influence the other qubit to be the same thing, 0, with the same probability. And here you get the same probabilities. The other one you get different probabilities.
So in the last one, yeah, if the left qubit was 0, then you see that the right qubit is in this state, versus if the left qubit was 1, it's in some other state. So depending on what the left qubit is measured to be, then the right qubit is going to be different. So entanglement meaning like my wife and I, right? Like we're entangled. We have a relationship with each other. Like if I'm sad, like that's going to affect her mood, versus if I'm happy, that will affect her mood. But if it's like a stranger who doesn't care if I'm happy or sad, we're not intertwined. We're not entangled at all. So then their state doesn't matter. So that's like this other one where their state is always this, half 0, half 1. They don't care if I'm happy or sad. So maybe that helps with the intuition or the terminology.
Still thinking the opposite, even with that example.
Does anyone have a way of explaining it?
Maybe think of it as the opposite of independent. So this is independent, right?
Yeah.
So entanglement's the opposite of independent.
Yeah, it's codependent, but when it's codependent, shouldn't the probabilities be the same? No?
Oh, it's not about the being the same or different. So here the qubit is half 0, half 1. Maybe I should have picked a different example. Half 0, half 1. But the point is like it's 50-50 regardless of what the first qubit was.
Oh, okay. Oh, it's 50-50. Oh, that's what you're saying. So you still have, doesn't matter what, if the first one was 0, the second one still has 50-50 chance of being 0 or being 1.
Yeah.
And then if you go to the previous one, does it favor the 0 then?
Yeah, so here if it was 0, you have a probability that the right qubit is 0 and a probability 4/5 that it's 1. Whereas over here, if the left qubit is 1, the right qubit has a probability of 8/11 of being 0 and 3/11 of being 1. So the probability of the right qubit here is different from the probabilities over here.
So its favor is 1 over the other. Okay, okay.
Would you like to give it a shot, Brian?
The way that I explain this to my students is that if you measure 1 qubit, it tells you something you didn't already know about the other qubit. And I think that works pretty good. I do want to caution one thing in terminology, which occasionally people do when talking about entanglement. Sometimes we use this word, this word of causality. I measure this qubit and it causes this qubit to be something else. As educators, we should erase that causal terminology from our vocabulary. It's something we inherited from our forebears many ages ago, and it has caused all manner of confusion. So it is not a causal thing. You can just say it's information that's being updated. You now know more about the other qubit than you knew before.
So I'm new to these concepts, and I'm trying to learn. But by picking up the first digit from most left, you're making everything else that's coming after that depending on that first digit, which means somewhat causality, I would say. You know?
So I think what's tricky is like sometimes in physics, causation is used in a very precise way. In terms of like the way it's used in everyday speech, there is an influence that maybe shouldn't be called causality, but you know, I think whether or not you want to use the word causes in a definitional sense versus like a vernacular sense I think people might fall on different sides of that.
So do you find, this is very intuitive, I like it, but do you find that this is maybe better than explaining separable state first?
So we do separable states and how to factor in and so we get into how do you prove that a state is entangled and stuff like that. I'm not talking about that here for time. Also note that this is already like, 70% into the semester. Like students have a lot more background at this point and are more comfortable with these calculations. Yeah.
So what Brian was saying is instead of using the word affects there, you should say is correlated to.
But it does affect in a way. Yeah, it still does affect.
It's not a physical thing, though.
It doesn't though.
No, actually it does.
Otherwise it's superluminal.
What I think no, it can. People sometimes use the term influence to try to distinguish between like an effect or cause that is limited by speech. But it gets into your interpretation of this, right? Of like locality and stuff like that. So it's like, in some interpretations there is an effect or an influence, like a collapse that happens faster than the speed of light, but you cannot transmit information faster than the speed of light, even with that. And so I think that this opens up a lot more than we want to get into.
Now a philosophy conference.
Yeah. Gina.
I have a I mean, this is very similar to how I would introduce entanglement. Although I wouldn't use this complicated of a state, I would choose one that's less.
Maybe something that's maximally entangled.
Right. So my question is why do you do the hard one first?
What do I actually do in my class? I mean, there's things I'm pulling from my class, right? So there's little snippets. So I'm like, what do I actually do?
Has a maximally entangled state.
Yeah. I mean, that's actually this that we're gonna do now.
Yeah, okay.
I don't remember well enough. Yeah. I teach this course every other year. So this past school year, I did not teach it. So it's less fresh. But this next school year, I'll teach it again. So. Yeah. So here's a question. Is the following state entangled? Well, we can measure the left qubit, and it's either going to be 0 or 1. It'll be 0 with probability a half. And then the state will collapse to this, which we normalize is just 0, 0. So we see that the left qubit was 0, because that's what we measured. The right qubit is actually also 0. Or the left qubit could be 1. That happens with the other probability a half. It collapses to 1, 1 after you normalize it. And so what we see is that not only did measuring the left qubit affect the right qubit, it completely determined the right qubit. So here, if the left qubit was 0, the right qubit is definitely 0. And if the left qubit was 1, the right qubit is definitely 1. So this is information that you've learned about the second qubit in the way that Brian was sharing about it. Like, if you know that you start in this state and you measure left qubit to be 0 or 1, you know that the right qubit is going to match it. And so in this case, there's like a perfect entanglement, a perfect intertwining between the two. And so we say that these are maximally entangled, whereas the other ones there's some influence, but it doesn't completely determine what the other qubit is. It just influences it more minorly. Any other questions about that? I mean, I guess a question for the audience. What do you do when students bring up these like philosophical questions and these interpretations and stuff like that? Like, yeah.
I'm kind of questioning, what is the best pedagogy for teaching entanglement? Because it is confusing.
Yeah, I think a lot of it will depend on your audience and what background they have leading up to it. Like I mentioned, at this point, we're pretty far into the semester, so I can push them harder on these things.
I'll go over a little bit more detail into violation of technical quality.
Yeah.
Students actually like the topic.
Yeah. Back there and over there.
I think actually it doesn't hurt to mention philosophy a little bit, because this is the kind of thing that brought up like the hidden variables controversies. So I think students can kind of lock into that.
Yeah, so in my class, we do also use IBM's quantum computer to show it violates one of the Bell inequalities. So we'll get a little bit into like the philosophy of it, but yeah.
Just quickly about people are having a conceptual issue with effect. Like it definitely is effect, and you should probably address this completely, sort of to make your class consistent. Disregard maybe these measurements of projections and sort of convey the notion of measurement in terms of projection, because effect is definitely the right term. It's not a philosophical.
Thank you. Yeah, Justin.
I've taught entanglement a few different ways. I've never really run into students who get bogged down and deep on like the causal relationship. You do the faster than speed of light thing that's been alluded to. I see a lot. And the only way I've ever kind of addressed it is do the Alice and Bob. And they measure them all, and they're totally random. And like, there's no way of knowing whether the other one's been measured or not. Your predictions and everything come out the same. They just happen to be correlated. So if Bob has made all their measurements, they would change their predictions of what Eve's or Alice's would be. There's no, order of operations kind of removes the causality in that.
Yeah, Megan?
On the physics philosophical front, for our high school program, we actually kind of lean into it a little. Like we don't have a formal, session on the philosophy not because they don't, understand or they're not smart enough or something. Like these are the questions that have formed the basis of a lot of these thoughts that we have.
Yeah. So one of the homework questions I give around this is actually to watch a YouTube video and I fill in the blanks. I do that quite a bit in my class. Yeah.
I just want to also follow up on the interpretations. Like, what do you do with it? I leave about a class period's worth of time in my schedule that I just have as leeway, because students will come up, like, I don't prompt the conversation, but when students come in with these questions, we take a pause and we explore it. And I think that it's important, especially because there are a lot of questions that don't have answers, and there are some questions that do have answers. And so then we also talk about, like, we can answer the ones that we have answers to, and these are all really good. And so I always recommend just building in time into your course to allow that to happen without feeling like you have to rush on to the next thing.
I'd be curious about the attractiveness of teaching quantum to different even the intersection with non-technical fields and areas. Like at my university, the University of Oxford, computer science and philosophy, that undergraduate degree has 40% women, but then computer science and maths has 10% women. It's just that there's not enough women applying. I mean, that's one of the main limiting factors. So it would be really interesting to know if there's more pathways for students, like at a young age when they're kind of deciding careers or even just getting exposure to think about quantum from other angles as well.
And if you want to get away a little bit from philosophy to electronic circuitry, you can think that entanglement has to do with hidden circuitry that you don't have access to, whereas classical physics would allow you to see the two different circuitries. Zero state would be one type of circuitry, and the one state another type of circuitry. And classically, those two circuits would be exposed. So I think in terms of electrical circuitry, you can present hidden variables kind of framework that's more concrete.
Yeah, with the understanding that there's not actually hidden variables. Yeah. Should we move on? We've had a lot of good comments.
I have a question.
Yeah.
So to better understand this, most significant bit is the left bit right here. And most significant, does it mean it's the most deterministic bit?
You could swap it and do the right. I just did left and right because left is. I started with left because it feels.
But if you do that,
more
the
normal.
whole process will be reversed, and you will start from the most right. Right? Everything will be the same. It's like Gram-Schmidt algorithm. Is it like that? Can you make an analogy?
I don't know.
In terms of like the information store, like so you don't have to define, what do they call it, big N? Like I don't think Dom or anyone's defined which encoding they're going to use.
Yeah.
So these are purely just abstract bits. How you encode info on it still is
Most
freedom.
significant doesn't have to be most deterministic.
No, there's no relation to the physical. Yeah.
But if it turns out that there's no entanglement when you measure the first bit, it should be a theorem that there's no entanglement if you happen to measure the second bit instead, right?
Yes, if there's only two qubits.
Yeah, or any.
Yeah, if we've had more qubits, it's possible that the first qubit's not entangled with the other ones, but the second qubit could be entangled with the other ones. Yeah.
I struggle with the question of how to introduce entanglement with my students. And it's a central thing because this is why we're all here, right? Because teaching quantum is different and more difficult from teaching other STEM courses. The way that I did it, so I'm a physicist, so I like to kind of start from more of a physics perspective. And there's a way that you can talk about like separability and non-separability without necessarily talking about these sort of non-local interaction kind of things, where you could say, state, and like how naturally measuring one thing, you know, changes the information about the other thing. I've found this as a way to kind of get around some of these philosophical issues, or at least push them back to later on, because understanding non-separability, which is really the mathematical property you're talking about here, is different from understanding the physical implications of physical entangled systems. Maybe that's helpful. I don't know.
Thank you, everyone, for your comments. Maybe we should keep going. Okay, so this state we saw is maximally entangled. If you know one qubit, that completely determines what the other qubit is. How do you create that state that's maximally entangled? Like, how do you make entanglement? Well, you can use quantum gates. So let's say we start off with two qubits that are both 0. What you could do is you can apply the Hadamard gate to the left qubit and do nothing to the right qubit. So the left qubit becomes this plus state here. The right qubit stays 0. If I multiply that out, it's 1 over root 2 times 0, 0, plus 1 over root 2 times 1, 0. So this is almost right. This 1 over root 2 0, 0 is right. We need this 1, 0 to become a 1, 1. So is there a quantum gate that will flip this 0 to a 1, but not flip that one? C naught. Because C naught flips the right qubit if the left qubit is 1. So this one gets left alone, this one gets flipped, and there's our maximally entangled state. All right, let's apply this to a problem of quantum teleportation. Okay, so in this protocol, there's two parties. Alice wants to send a qubit in some unknown state to Bob. So the fact that it's unknown matters. If it's like the plus state, she can just call Bob on the phone and be like, hey, Bob, make a plus state. And Bob's like, okay, I can do that. The idea is that she doesn't know how it is, and she needs to send it to Bob somehow. And so we're going to assume that she can only send classical information. So she can't take the qubit, put it in a box, and like FedEx it to Bob. But they do share entanglement. So the idea is Alice is over here. She has this qubit in some unknown state. So some amplitude times 0 plus some other amplitude times 1. And she doesn't know what it is, so she can't just tell Bob what it is. We're going to call this state psi. That's the general variable we use for a quantum state. And besides this qubit, Alice and Bob have this entangled pair of qubits in this maximally entangled state. So these two qubits are maximally entangled. So Alice has two qubits, this one that is unknown, and this one that's entangled with Bob's third qubit. So there's 3 qubits involved here. So if I want to write the state of all 3 of these, I can just multiply them together. So this is technically a Kronecker product or tensor product, but we don't write it a lot of times to be lazy. And now I can distribute this. So this would be alpha over root 2 times 0, 0, 0, plus alpha over root 2 times 0, 1, 1, plus beta over root 2 times 1, 0, 0, plus beta over root 2 times 1, 1, 1. So this is the state that we're starting off with. And they're going to try to do something to make it so that Bob's qubit becomes in this state alpha 0 plus beta 1. That way Bob's qubit now has that information. So what Alice is going to do is she's going to apply a C naught to her 2 qubits, which are the left 2 in the way that we've written it. So if she applies a C naught, this 0 will get flipped to a 1, and that 1 will get flipped to a 0. So we're going to get that state. I'm pausing because people are taking pictures. So. Next, Alice is going to apply a Hadamard gate to her first qubit, so the one on the left. So that's going to turn this into a plus, that into a plus, that into a minus, and that into a minus. And if I write out plus, that's a plus state, that's a plus state, and then write out minus, that's a minus state, that's a minus state. And I can distribute all this, multiply it all out, and we're going to get this. And I factored out a 1/2 from everything. All right, I'm going to copy this. I'm going to simplify this a little bit. So if you look here, in this state, Alice's 2 qubits are both 0. And over here, they're also both 0. So we're going to factor that out and then we have alpha, right qubit is 0, and then beta, right qubit is 1. Similarly, Alice's 2 qubits could be 0, 1, so we can factor that out, and we get that, and then they can be 1, 0, we get that for Bob's qubit, and then 1, 1, and then we get that for Bob's qubit. So let me copy that over here. So now Alice is going to measure her 2 qubits, because she can't measure Bob's, so she's measuring hers. So she measures her 2 qubits. She's going to get that they're both 0, or that they're 0 and 1, or 1, 0, and 1, 1. And each of those will happen with probability 1/4, because you take the norm square of that 1/2. So it's probability 1/4. She gets each of those outcomes. And then the state's going to collapse of these in each of the cases. And so if she got 0, 0, you see Bob's qubit is now in the state alpha 0 plus beta 1. So Bob's qubit is now in the state that Alice wanted to teleport to him. So if she got 0, 0, Bob doesn't have to do anything. He's got the state. If Alice got 0, 1, you see that Bob's qubit is close, except this 1 needs to be a 0, and that 0 needs to be a 1. So what does Bob need to do? Apply an X gate or NOT gate to flip it. So if she got 0, 1, Bob applies X, and that will flip this, and that will now be the state that she wanted to send. If Alice got 1, 0, Bob's qubit is almost right, except it has a minus sign here for the 1 state. So how can we flip them? With a Z gate, and that will fix it. And then if Alice got 1, 1, then Bob's qubits are off both by a bit flip and by this minus sign. So how can Bob fix that? He can buy both X and Z to fix it. So the idea is Alice will measure her qubits, and depending on what outcome, she'll call Bob and be like, hey, Bob, you need to apply an X gate. Or, hey, Bob, you need to apply a Z gate. Or you need to do nothing. Or you need to apply X and Z. And then Bob will do it, and now she has teleported the state over to Bob. And so you can see here that this can't happen faster than light, because Alice has to call Bob. This is a classical communication, and which is bound by the speed of light, in order to tell him what he needs to do, whether it's nothing or apply some gates. And so so you can already see from here that just because you have entanglement doesn't mean you can teleport information faster than light. Any questions? Yeah.
How far in the course do you get to this topic?
I mean, I could check my syllabus, I guess, or just check the textbook, see where it lands, right? Yeah. Yeah.
So I'm thinking you make it very clear in the book that so the teleportation is not like the qubit travels from one place to another, it's the information.
Yeah, it's information. So Alice never physically sent her qubit. She still has her 2 qubits. Bob has the 3rd qubit, but the information transferred.
Bob is already and that's from what Brian was saying before, like the information gets influences sort of the information in the entanglement, right? So I think the information word might be key for this explanation. But my question is, so Alice measures, I just want to make sure I understand this properly because it's a little confusing. So Alice eventually measures her 2 qubits.
Yeah, so
And then based on what she gets on her measurement, she knows which gate would need to be applied in order for Bob's qubit to turn into the same.
yeah, because she knows depending on what she gets, the state has collapsed in one of these 4 options. So if she got 0, 0, she knows Bob's qubit is correct. If she got 0, 1, she knows that Bob's qubit needs an X gate in order to make it correct.
But she still does not know what Bob's qubit has right now. Because
She
she's not measuring.
does know that it's in the superposition.
So Bob had to measure.
No, if Bob measures his qubit, he'll just get 0 or 1, and it'll collapse the state. So,
She measures both of her qubits.
yeah, so she measures the left 2. So she's either going to get 0, 0, or 0, 1, or 1, 0, or 1, 1. Bob's qubit is going to be in one of these 4 states.
But we don't know which of them.
We do know because it's going to be, it's going to depend on what Alice got. So if Alice got 0, 0, she knows it's this one. If she got 0, 1, she knows it's this one.
And that's from the calculations that you calculate.
Yeah, it's from this. So if you take this one happens probability 1/4, and that's just this. This next one happens with probability 1/4, and that's this one. And then that one, and then that one.
Okay, so yeah, so Bob doesn't need to measure anything. If she
Yeah,
measures this,
Bob shouldn't measure anything. Then he just ruined his state.
Exactly. So she gets, let's say she gets 0, 1. Now, based on that calculation, she knows that Bob is in that state.
Yeah.
Alpha plus beta, alpha 1 plus beta 0. And then based on that, she knows which matrix to apply.
Yeah.
And so then
No, Bob knows which one to. Bob applies it. Yeah. I mean, you can assume that Bob knows the protocol. So Alice could just be like, hey, Bob, I got 1, 0. And Bob's like, okay, thanks. And then Bob would be like, okay, I need to apply a Z.
So this is like a little lookup table. That's why you did all the
Yeah.
calculations to make this lookup table.
Yeah.
Okay, thank you.
Only one bit is being teleported. The other one of Alice's bits is already entangled.
Yeah, so the state of 1 qubit is being teleported. So the state of it. So neither of these qubits are physically leaving Alice's possession.
So, well, would it be right to say they both have, they each have one, there's one like shared entangled
Yes.
qubit.
Well, it's a pair. Yeah, it's a pair of entangled qubits.
Then there's one other one.
Yeah.
Yes.
Yeah, so by leveraging this entanglement, Alice can do stuff to influence Bob's qubit to become alpha 0 plus beta 1, perhaps with some gates that Bob needs to apply. All right. One thing I want to point out is if you look at Alice's 2 qubits, if her right qubit is a 1, that means Bob needs to apply x. And if her left qubit is 1, that means Bob has to apply z, perhaps as well as x. So this is kind of like a conditional thing. So if Alice's second qubit is 1, Bob applies x. If Alice's first qubit is 1, Bob applies z, perhaps z as well as x. So what we can do is we can simulate this quantum teleportation protocol now. And we're going to simulate it in this browser-based simulator called Quark. And so I guess if you want to get your laptop out, you can, or you can watch me do it. So this is made by a Google researcher. Oh, wait, I don't have internet. Let's not worry about it. But basically, this is drag and drop simulator. So you can be like, okay, I want to create a qubit in some like funky state. So I'm going to use a square root of y gate that rotates around the y-axis by 90 degrees. A t gate, I haven't told you, that rotates around the z-axis by 45 degrees. Hadamard gate. If I do that, my qubit ends up here in the northern hemisphere, so some like whatever state. And I want to teleport this over to Bob. And you can see that we're going to be successful in doing that. Alice and Bob are going to share entanglement between these 2 qubits. So they're both 0, 0. How do we make entanglement? Well, we can apply a Hadamard gate and a C0 gate. So we saw that for how to create entanglement. And so now these 2 are entangled, and this qubit is in some state that we want to teleport to Bob. So now Alice is going to do her 2 things. She's going to apply a C0 gate. I should note, this is the control, and this is the NOT gate. So this, you apply a NOT if this is 1. That's what that means. And then she's going to apply a Hadamard gate. And then if her right qubit is 1, Bob will apply an X gate or a NOT. And if Alice's left qubit is 1, Bob will apply a Z. And the result of that is that Bob's qubit is now what Alice originally had. And Alice's qubit is no longer in that same state because, I guess I'll tell you, you can't copy or clone arbitrary quantum states. So there's this theorem that, so basically for Alice to give that state to Bob, she has to lose it herself if it's unknown. If she knows what it is, again, hey, Bob, I have a plus state. Can you make some plus states too? Now everyone has a plus state, okay? So like that's not the issue. It's that if she doesn't know it, you can't just make copies. So this is a tool that you could use in class. I use this a lot because the interface is just so clean for dragging and dropping. You can also have students run this on an actual quantum processor. So one of, like, for example, IBM's prototype quantum computers. Many companies have their quantum computers available on the cloud now. And so their interface looks like this. Again, it's drag and drop, just a little more cumbersome. But you can run it on an actual processor, and you can see on this particular processor, let me back up. This state that Bob should end up with, it should be 0, 14.6% of the time, and 1, the remaining 85.4% of the time. And so if you actually run this on one of Ivan's quantum processor and you run it 1,024 times, you don't get quite that 85%, and you don't quite get that 14%. It's because the processor's not perfect. There's some noise and stuff in it. So it's not quite what we expected. So that should be 85, right? Yeah. It's not normalized. There's anyways. Okay. Are we on time? Okay, we can keep going. So we've seen here that real quantum devices have error. Yeah.
Just before that you get to error correction, if you can go back to the circuit, because I really.
This one or the previous one? This one?
Oh yes. So why is the bottom, the third qubit, third line is Alice's qubit that she wants to teleport.
Yeah, she wants to teleport this to Bob, and we can visualize this because this is just a simulation. We're not like doing an experiment, because if you measure it, you'll destroy your qubit.
Right.
So.
But that's exactly my question. Like,
Yeah.
so why does she have to apply those 3 gates?
Oh, I'm just trying to make some fun state to teleport.
That's what it is.
Yeah.
Okay, so that's that. So you could have been.
It could be anything. Yeah.
But some gates will create some state, and we're teleporting.
Yeah.
Oh, all right, thank you. So yeah, that was a short question.
No problem.
Clarifies it.
Yeah. I mean, we're all here to learn, so. All right. So we've seen that quantum computers have noise, have errors. And so does that mean we can never build a quantum computer, or are we okay? So this question is something that many people work on. But I like how John Preskill from Caltech has framed this, which is that, is building a quantum computer just really, really hard, or is it like ridiculously hard, like impossible? And so he posed this as a question. And what he means by this is it something that is surmountable, or is it effectively impossible? And this really comes down to a question of the errors. Like, if the errors build up and there's no way to fix them, then how are you going to be able to do a computation well and get some meaningful results out of it? And it turns out that because of the discovery of quantum error correction, that there are ways to fix the errors as long as the errors are low enough. And that's true with classical computers as well, right? There's errors in them, and so you can do all sorts of error correcting codes in order to work around those or to fix those errors. And so you can do that in the quantum case with qubits as well. And so classically, the only error you can have is a bit flip. You have a 0 that accidentally becomes a 1, or you have a 1 that accidentally becomes a 0. And perhaps one of the simplest ways to make it so that these bit flips don't cause any problems is you can do, I guess I'm going too fast. Actually, there's this good Veritasium video. I don't know if you guys know Veritasium. He's a popular YouTuber where he talks about this, the effect of cosmic rays and how it causes bit flips in computers and stuff like that. And this also affects quantum computers. But he has all sorts of historical anecdotes, like an election in like a Dutch election or something like that, where someone got more votes than they should have because like a bit flipped, and you could tell like which bit it was by how many additional votes there were and things like that. And apparently, you remember old Windows computers? They would get the like blue screen of death pretty often. That those are most often caused by cosmic rays, actually. So you're having these bit flips that are occurring. So this is a great video. My students have to watch it as part of their homework, fill in the blanks and stuff. But anyways, so what we can do is we can use an error correcting code where we take each logical 0 or 1, and we use many physical zeros and 1s to represent that. That way, if one of them gets messed up, we can still figure out what it was supposed to be. And so perhaps the simplest way is to just have many copies of your bits. So instead of having a single logical 0, we have 3 physical zeros. That way, if one of these flips and becomes a 1, we can go, hey, why is one of them a 1? I think that should be a 0, and you can flip it back. And similarly, instead of having a single 1, you can have 3 ones. And so, for example, let's say we have 0, 1, 0. Again, that 1 probably shouldn't be there. It should probably be a 0, so you can correct it to 0, 0, 0, and so forth. And so it turns out that there's a quantum version of this that was discovered by Peter Shor, who's the same person that discovered that quantum computers can factor efficiently. In fact, the history is interesting, right? He came up with this factoring algorithm first, and people are like, oh no, is this going to break all of our computer codes, right? And some people are like, we don't have to worry about it because the noise in quantum systems, like, there's no way you could ever build one of these quantum computers. And so, like, the next year or something, Peter Shor was like, hey, I discovered a way to do error correction. And people are like, oh, shoot. Well, and then our field, got lots of funding. All right, so quantumly, we can also protect from bit flips just by the same idea. Instead of having a single qubit be 0, we can have 3 physical qubits represent a single 0, and 3 physical qubits all in one representing a single logical 1. Sorry, what's that?
We have something in electronics called TMR, triple modular redundancy.
I'm not familiar with that.
It's like repeating same thing 3 times.
Okay. I heard yes, so yeah. In general, of course, a qubit is in a superposition of 0 and 1. And so physically, that would be alpha times 3 zeros plus beta times 3 ones. And so let's see how we can correct error. So let's say we have a bit flip in the left qubit. That means that this nice pristine state becomes corrupted. So that 0 becomes a 1, and that 1 becomes a 0. So the idea here, well, let me back up. So if we were to just measure the qubits, what we would get is we would get that the 3 qubits are 1, 0, 0 with probability the norm of alpha squared. Or we would get that the 3 qubits are 0, 1, 1 with probability the norm of beta squared. And the state collapses, and we lose the superposition. So we don't want to just measure the bits and be like, hey, look, there's an error here. This qubit is off from the other 2. Because by doing that, we've lost the state that we wanted to encode. So quantum error correction has to be a little more sneaky, because you don't want to just directly measure what your qubits are. And so what we do is we can instead measure the parity of adjacent qubits. And what I mean by parity is whether the number of 1s is even or odd. And so 0, 0 has even parity because there's an even number of 1s. There's 0 1s. 0, 1 has odd parity because it has 1, 1, which is odd. Here, this has 1, 1, which is odd. And this has 2 1s, which is even. So, and what you can see here is that even parity corresponds to the 2 qubits matching, and odd parity corresponds to them differing. And so again, even qubits parity means that they match, odd parity means that they differ. And so let's see how we can apply that to this state where the left qubit has flipped. So if we measure the parity of the left 2 qubits, so let's go ahead and label these qubits just so I can give them a name. Let's call these Q2, Q1, Q0. And I'm going to measure the parity of adjacent qubits, so the parity of the left 2 qubits and the parity of the right 2 qubits. So if we measure the parity of adjacent qubits, what we see is that here the left 2 qubits have odd parity, they differ, and here the left 2 qubits also have odd parity, so because they again differ. And then the right 2 qubits, those have even parity, they match. And here the right 2 qubits, they have even parity, they match. And so with probability 1, we'll find, again, the parity of the left 2 qubits is odd, and the parity of the right 2 qubits is even. And the state doesn't collapse to anything because we're not forcing it into one or the other. They both have the same parities of adjacent qubits. So the state is unchanged. We're able to measure parity without collapsing our state. The textbook, we give like a circuit for how to actually do that, and students simulate it and all that. But this is enough for now. There's a way to do this, and it doesn't collapse your state. And so now you know the left 2 qubits don't match. The right 2 qubits do match. Where's the bit flip? It must be in the left qubit. So you can apply an X gate to the left qubit, and that corrects your error. So now you have your nice state again. All right. This was assuming that the error we had was a complete bit flip. So a 0 completely turned into a 1, and then the 1 completely turned into 0. But you might just have a partial bit flip. So what I mean by that is a full bit flip means that your state goes from 0 to 1, and 1 goes to 0 directly. So the north and south poles are jumping between them. But in a quantum computer, you can have any change in latitude correspond to a partial bit flip. So instead of being entirely 0 or entirely 1, you went from entirely 0 to mostly 0, but a little bit 1. And that still constitutes an error. And so we're going to investigate now, what do you do with partial bit flips, and where you have any change in latitude. So a partial bit flip is going to correspond to this. So your 0 becomes a combination of 0 and 1 instead of becoming entirely 1. And then your 1 becomes a combination of 0 and 1 instead of becoming entirely 0. So epsilon tells you the because epsilon squared is the probability of a complete flip, if that makes sense. The I's are to make this a valid quantum evolution. So if we start off with this nice state and the left qubit has a partial bit flip, this 0 turns into this combination of 0 and 1, and this 1 turns into this combination of 0 and 1. And now if I just multiply everything out, I get this. And now we can ask, which we can reorder so that it's in numerical order, like counting from smallest to biggest in binary. And now we can measure the parity of adjacent qubits and see what happens. And so now, because there's more states, different things can happen with different probabilities. And in general, there's 4 possibilities. The parity of the left 2 qubits and the right 2 qubits can both be even. You can have even and odd, or you can have odd and even, or you can have odd and odd. And so we're going to investigate each of these one by one. So I'm going to recopy this state over here. And let's see the probability of the parities being even. So that will correspond. So here the left 2 are even, they match. Here the right 2 are even, they match. Here that's odd, so we're not looking at that one. That's odd, we're not looking at that one. Here they're even and even. So the probability is going to come from this first state and this last state here. So the probability is the norm of those squared summed together, which simplifies to that, which simplifies to that. And the norm of alpha squared plus the norm of beta squared must be 1, because the total probability should be 1. So it's probability 1 minus epsilon squared. You'll find that everything is even. And when that happens, the state is going to collapse to these 2, which we then have to normalize, which just gives us alpha times all zeros plus beta times all 1s, which is the state that we want. That's nice and without any errors. So what we see in this case is that if we measure even for both of those, that means the state collapsed into 1 where everything agrees, and that actually corrected the error. So in this case, it's possible that we didn't even know there was an error because the measurement in itself actually fixed it. Another possibility is you can, well, actually this happens probability 0. You can't have the left 2 be even and the right 2 be odd, if you look at all of these. This never happens. You can have the reverse, though. You can have the left 2 be odd, like here, and the right 2 be even. And also here, the left 2 are odd and the right 2 are even. So the probability will correspond to those coefficients norm squared added together. We can simplify that to just being epsilon norm squared. And then the state will collapse to these 2, which we can then normalize. And you can see here that this state is not exactly what we want. We need to fix it. What do we need to do to fix it? Well, actually, let me say, well, you can see what happened after the measurement is that here, we want this to be 0, 0, 0, and here we want this to be 1, 1, 1. So we have a complete bit flip now, or full bit flip that we saw earlier. And we can correct this just by applying an X gate to the left qubit. And so we're fine. And so what we're seeing is that by measuring the parity, you force it to collapse into a state where everything agrees and that corrects the error, or you force it into a state where they fully disagree, at least for the left two qubits, which is now a full bit flip. So you force it from a partial bit flip into no bit flip or a full bit flip. If there's no bit flip, you don't have to do anything. If there's a full bit flip, you apply an X to fix it. And then the final option of them both being odd can't happen. So those are the only possibilities. You force it to have no error, or you force it to have a complete error that you can correct. You can do the same thing with phase flips, because remember in quantum, it's not just your latitude that matters, it's also your longitude. That is a different state for your qubit. So for example, going from plus to minus would be a full phase flip. Or you can also have a partial phase flip where you go around you change your longitude some smaller amount. And there needs to be a way to correct for this. It's pretty similar to before where, but instead of using 0 and 1, we use plus and minus. So instead of having 3 zeros, you have 3 pluses and 3 minuses instead of 3 ones. Because plus and minus are like opposite sides when it comes to phase, versus 0 and 1 are opposite sides when it comes to your bit flip. Yeah.
Super quick, when you said in your third case, when you say that it collapses to this state,
Yeah.
is that because the terms that you dropped out don't satisfy the parity condition?
Yep.
That you're okay.
Yeah. All right. So generally, you have a superposition of 0 and 1. So it'd be a superposition of 3 pluses and 3 minuses. And then you can do the same thing where you measure the parity, except instead of the number of ones, it's a phase parity, which is the number of minuses, if it's even or odd. So it's the same idea where even parity corresponds to them matching, and odd parity corresponds to them differing. You're allowed to do this. In the textbook, there's a circuit for how to actually do it. And now to fix a phase error, you will apply a Z gate instead, because the Z will turn plus into minus and vice versa. So basically, it's the same thing as what we had with bit flips, except you use plus and minus and use Z instead of X to fix it. And so what Shor discovered was that you can put these together, where you start with a phase flip code. So you have a 0 is 3 pluses, and a 1 is 3 minuses, which you can write out a plus is 1 over root 2 0 plus 1 over 2 1, so you have 3 of these. And the same thing with minus, you have 3 of these. So this will allow us to correct phase flips. And now we can layer on the bit flip code. So this 0 will replace with 3 zeros and 3 1s. This will be 3 zeros and 3 1s and 3 zeros and 3 1s, like that. And now this can both correct bit flips and phase flips. And so you can, and this involves 9 physical qubits for each logical qubit. And you can detect the bit flips, again, by measuring the parity of adjacent qubits, and phase flips by measuring the parities of this triplet compared to that triplet and so forth. Yeah. All right, so this was the first quantum error correcting code that Peter Shor came up with. But there's actually many, many more. There's a whole zoo of them. You can go to this website, errorcorrectionzoo.org, which is a collection of error correcting codes, both classical and quantum. Last year, when I gave this intro, there were 791 code entries. 424 of them were quantum. As of this morning, there's now almost 200 more codes, and a little over 100 of them are new quantum codes. And so this is a huge field. And in some sense, the whole field depends on this. Can you correct the errors? And the better codes you have, the less your hardware has to be good. So, yeah.
Do you have any recommendations on what's the best error correction code to introduce to students?
I just do the short code. I don't do stabilizer formulas or anything like that. There's no way am I doing group theory. I just do this shortcode.
So you don't find the stabilizer is a little too
I don't do that at all, no.
too complicated.
If they don't have linear algebra, they're not going to handle a group. Yeah, and I want them to get the idea of it, right? This captures a lot of the ideas, except the other codes, instead of measuring parity, it might be some other thing, and how you correct it might be different, and yeah. Was there another question?
Are there codes that use code words?
Are there codes that, I mean, these are code words, right? When it had like 000 in place of 10, that's a code word. So, yeah.
Okay.
Yeah. Yeah.
So some books cover chapters in error correction, and then I was expecting to see one in your book, and I was like, oh no, he only did shorts. But I think that's enough, because often those chapters are towards the end of the book, and people don't get to them anyway.
Yeah.
And this is sort of snuck in the middle, which is even better. But I have an actual question of why does he need 9 bits? I did not grasp why he needs.
Oh, it's because you need 3 to do the phase, and then each one of those 3s turns into 3 in order to do the bit flip. So that becomes 9. Yeah.
When you do these more complex error correction in actual systems,
Experimentalists, I need help.
aren't you collapsing states? I mean, wouldn't you be introducing noise?
Would experimentalists like to talk about what you physically?
Aren't you actually making physical measurements when
So
you...
you're projecting to either the errors occurred or not, so it collapses it to I know
But
there's an
I
error and I
was
can fix
thinking
it.
if you collapse the state, you have to connect it to a classical system, and that might introduce noise.
Yeah, there's always noise. I think isn't that why there's thresholds?
Yeah.
It's like you have to be able to do these things at a certain level before you're adding more than you're fixing.
Yeah.
I don't know
Yeah.
what those are.
Maybe I'm expanding on that. You have extra ancilla, so extra qubits that don't store your logical information, and then you do entangling measurements to those. So you like do CNOT gates between your logic, like your physical qubits where the logical information is stored, and then to these ancilla like extra qubits. So you're measuring those extra ones, and so that's why you don't collapse the logical information in those encoded in those physical qubits that
I
are
see.
not the
So you're
ancillas.
sort of insulating the actual qubit.
Yeah. You basically do something with the qubits that you care about, so that way the parity information can be read from like an extra qubit, and then that makes it so you're not ruining your normal qubits. Yeah. I guess in the book, if you see the actual circuit for how to measure parity, maybe it'll make more sense. It's so hard because like there's so much we're skipping, right? Yeah.
I'll just add one more sentence hopefully. It's like the extra qubits, these ancillas, they can have errors from those measurements. And so the act of doing those errors can cause more errors in your system. You're introducing more noise. But those measurements, if you have errors on the ancillas, you can have even more ancillas to detect those kinds of errors. And you can also do those measurements multiple times. So even if you have high measurement error systems, like superconducting qubits or something, you can still just do the measurements multiple times and be confident in which was the actual correct measurement result just by repeating those
Yeah.
measurements.
But I thought the probability P was the bit flip, for example, is smaller than 50%. You don't need extra P. Mathematically, if the probability of the bit flip is less than 50%, right? So by doing this majority rule, you can always correct the error. I don't think you need more than 3.
Oh, these qubits are to measure those parities. So these extra qubits
Oh,
are...
for the parity.
Yeah, so they don't store information, but you calculate the parities by
Yeah.
doing the CNOT gates from those 3 qubits to the extra ones, and then measuring that tells you the parity.
And maybe the like takeaway for this is that quantum error correction is a huge field within quantum information science, and so there's a lot of complexity that you can get into, and many PhD theses for each of these codes, and yeah.
So one thing is that it's a partial measurement, right? You're measuring parity, but you're not actually measuring.
Yes, and so you're not actually
question I have.
Why don't we take a break? Yeah.
Well, I'm curious of the people that are teaching quantum, have you taught logical gates in your intro courses?
No.
Classical what?
No, I'm sorry. Quantum, like you have logical qubits, and then to use those logical qubits, you need a different kind of gate.
Yeah. No, I don't.
What kind of examples did you have in it?
Well, like how do you implement a CNOT across two logical qubits?
Yeah, it's more like quantum error correction is a thing. You know, you can study it in grad school if you want, and let's continue on to see some algorithms.
Is there a good source of how it's actually been implemented and how successful it's been in the real world?
So I think the past year has been a really exciting time for this, actually. There's been several experiments that have shown that by using error correction, they're actually able to lower their error rates. And so at least just for like storing quantum information, like storing the state of a qubit, and if it starts to get messed up, they can fix it. It doesn't have all the rest of the things you need, like applying quantum gates to these logical qubits and things like that that you need for a full-fledged quantum computer. But we're starting to see that these quantum error correction protocols work in the lab. And which code you use depends a lot on what your hardware is, in terms of what qubits are able to talk to each other and stuff like that. Yeah.
Do you have any plans for kind of an expansion pack on qubit touchdown that deals with error correcting qubits?
I mean, I've heard it come up from various suggestions. Another expansion pack I've heard was to have a second board that you add, so you have two qubits and they can be entangled and stuff like that. But how to do it, I don't have a really good idea yet. Yeah.
Yeah. You make the students think
Yeah.
about it.
I think there's a game that was presented or will be presented at the quantum QC conference, the Quantum Science and Engineering Education Conference, on a game for quantum error correction.
Oh, nice. Okay, should we take a break for a few minutes? Sure. How about we come back 12:15, so 7 minutes.
If I was building a quantum computer, I just simply wouldn't make
I think we're going to reconvene. I think we're going to reconvene.
They pop up in some secret.
Where is Justin? I guess I shouldn't start until Justin's here. Yeah. Oh, yeah. Oh, that's true. Oh, I just saw Justin, and then he ran off again. That's fine. It's fine. And I see Justin coming back, so we're almost ready to start. Yeah.
All right. Got the last actually section for lunch, and then we'll have lunch. So just continue on with Tom's great intro.
All right. So one of the breaks, I thought of something that I should have mentioned, which is what my teaching load is. So we're on the semester system. We're on a 3-3 teaching load, so 3 classes per semester. So generally, I'll teach general physics for the life sciences because there's so many like pre-med students, and then like an upper division physics class, and then maybe either another upper division physics class or like another section of general physics. So yeah, and then this course is taught as a special topics course every other year. And then there's actually a new course that I'll be teaching this fall, which is called Quantum Physics and Technology for Everyone. So this is going to be a 100 level like core class for the students that need a science course as part of their bachelor degree requirements, but are like not into the sciences. And so this is going to be a conceptual introduction to quantum mechanics, like the different properties of quantum mechanics, how they're applied to existing technologies, and how they might be applied to emerging technologies such as quantum computing. So that is to make it really hands-on, do lots of like arts and crafts and things like that. Basically like hands-on at the level that a theorist can do hands-on. That's why I said like arts and crafts. And so, yeah, I was originally going to teach this class in 2021, but then I went to serve in the government for a little bit, and so now I'm going to have my opportunity to teach it for real. So, yeah. Okay, so I'm excited to get to this section, because this section I actually had prepped for last year, but we ran out of time, so we didn't cover this at all. So for everyone, this should be new. So we're going to be looking at a couple of different quantum algorithms. The first one is how do you add numbers with a quantum computer? And the second one will be how do you a way to calculate parity. And this is different from the parity stuff we were just talking about before. You'll see when we get there. Okay, so adding numbers, let's just start with normal classical pen and paper adding numbers. So let's say we want to add 11 plus 20. Wait, why does it say 25? 35 in binary. Okay, so that should be the number 11 in binary and the number 24 in binary. And then, yeah, I need error correction. See, if I taught this last year, then we would have caught it and I would have fixed it. So, Okay. So when you add by hand, you start at the right and you do 1 plus 0 is 1.
Is that 26? It's 14.
Sorry.
24 should be 14.
Oh, this should be a 14. Oh, that makes sense because this only has 4 bits. Thank you. 14. We have found the typo. So then you carry a 1. And then you do 0 plus 1 plus 1 is 2, which is 1, 0. So it's 0, you carry a 1. 1 plus 0 plus 1, again, is 2, which is 1, 0. So it's 0, you carry the 1. 1 plus 1 plus 1 is 3, which is 1, 1. So it's 1, you carry the 1. So there's the answer. So that is 25. So again, 11 plus 14 is 25. So to label each of these bits, we're just going to look at adding 4-bit numbers just to make it simple. So our first number, we're going to write it as A3, A2, A1, A0. And then our other number in binary is B3, B2, B1, B0. We have a number we can carry in. So implied in the first one is a carry in of 0. And then there's all the subsequent numbers that we carry. So those would be C0, C1, C2, C3, C4. And then when you add them, you get each bit of the sum. We'll call those S0, S1, S2, S3, S4. And S4 is just that fourth carry. So C4 equals S4. OK. So one way to do this is by using something called a full adder. So what a full adder does is it basically handles this column by column. So you have a bit that you're carrying in, and then the 2 bits of A and B that you're adding. And the result will be a bit of the sum, and then the next bit that you carry out. So just abstractly, just classical computing, think of this as some logic circuit, some circuit element. It's taking in your carry bit, the 2 bits you're adding together, and you get a sum and a carry out. And what you can do is you can string together these full adders. So initially, we're adding our carry in is 0. We have our rightmost 2 bits. If we add those together, that will give us the first bit of the sum. And then what carries out of this becomes the carry bit into the next full adder that we then add with the next 2 bits to give us the next bit of the sum. And what it carries out becomes what is carried into the next full adder. With the next 2, you get the next bit of the sum. The next carry out, that becomes the carry in for the next full adder. Added with the last 2 bits, you get a bit of the sum, and then the final carry is your leftmost bit of the sum. And so by stringing these full adders together, you're able to generate your sum. So this is one way that you might do it classically. Who has like a computer science, computer engineering, electrical engineering background where, yeah, I saw a lot of nods, so this should be familiar. This is covered in the first chapter of my textbook on classical computing because I'm anticipating when we get to quantum, we're going to do the quantum version of this. And for my students who are not engineers, they need this all spelled out from the beginning. So yeah. OK, so how do you actually make one of these full adders? Well, you can make a full adder using logic gates. And so how many of you have seen logic gates before? I don't know, how much do I need to review this? I think everyone seems OK with it, actually, for the most part. So basically, if you have A and B, you take the exclusive OR of those. You take the AND of them. For the exclusive OR, you AND it with the carry in. With those, you OR to get the C out. That you get the sum. Basically, there's some known circuit, right? In my textbook, we talk about how to actually do this and get it from like a truth table and stuff like that. Maybe I should mention, I was also a computer science undergrad. That's why my research is quantum algorithms, because my PhD's in physics. And then for my computer science undergrad, we did some computer engineering courses. So, OK. So what we want to do is we want to take this full adder circuit, and we want to turn it into a quantum circuit. But one of the things is that a logic gate may not be a valid quantum gate. A quantum gate has to correspond to a unitary matrix. It has to preserve what the probability is. And so you can't just replace it directly. It needs to be, it's a little bit more complicated than that. But one of the nice things is that there's a field of classical computing called reversible computing, which is basically how do you make classical logic gates that are reversible. And it turns out that all reversible gates are unitary. So if you have a reversible gate, that is a valid quantum gate. And again, in the textbook in chapter 1, we go into reversible computing and everything. So you can think of it as like chapter 1 is classical computing and kind of picking from different areas of classical computing the ones that will be relevant for quantum computing. And so there's actually reversible versions of all of your standard logic gates. So for example, the NOT gate, that actually is just a quantum gate. That's your X gate. An AND gate is not reversible because if you know that, let's say the AND is 0, you don't know what the inputs were. Like were both inputs 0, or was one of the inputs 0 and the other one 1, and which one, and so forth. So you can't reverse an AND to figure out what the input was from the output. But you can reverse what's called a Toffoli gate. This is a controlled NOT. So remember C0 is a controlled NOT. This has two controls. So if A and B are both 1, then it flips the last bit. And if your last bit is 0, that will give you the AND of A and B. And this is reversible. An OR gate, you can use an anti-Toffoli, which flips if A and B are both 0. And as long as that the bit you're flipping is 1, that gives you an OR gate. An exclusive OR can actually be made from 2 C0s. I don't expect you to like understand just by looking at this like why this is true and stuff. But in a course, you would do all this much more slowly. You can do a NAND gate and a NOR gate, similarly as well with a Toffoli and an anti-Toffoli gate. So I'm going to stick that in the corner so we can refer to it. And so what we're going to do is we're going to replace each part of this full adder with its reversible version, which is a quantum version. Because again, reversible gates are valid quantum gates. And so let's go through this bit by bit. So here, we're taking the exclusive OR of A and B. And exclusive OR can be done using 2 C0s. And so that's what we're doing here. So with these 2 C0s, this qubit that started off as a 0 is now the exclusive OR of A and B. Next, we're going to do this other exclusive OR of the carry-in and the result from this exclusive OR. And so we can do that with these 2 C0s. So we're taking a C0 from this exclusive OR of A and B and also with Cn. And that will give me the exclusive OR of all of those. And that is now the sum. So that one is taken care of. We have this AND gate here in green. And the AND gate can be done with this Toffoli gate, with this control NOT gate, which is what we have here. So now this qubit is the AND of A and B. We have another AND gate here, which we can do with this control NOT, or this Toffoli gate. And then we need this OR gate at the end, and an OR gate is this anti-Toffoli gate that looks like that. And we want the input to be a 1, so we're going to flip this 0 to a 1 using an X gate. And so this is a reversible version of your full adder, and so you can string these together and make your circuit for adding numbers. Any questions about that? The textbook actually talks about 3 different ways to make this quantum, but this is just, here's one. Okay, the next thing we want to look at is an algorithm for calculating the parity of 2 unknown bits, where you access the bits through an oracle or a function or a black box. And so basically, there's this function f of x where if I evaluate f of 0, it gives me bit b0, and if I evaluate it at 1, it gives me bit 1. And I'm trying to find the parity of these 2 bits. And so the idea with these types of problems in computer science is we're trying to solve these with as few queries to the oracle or with as few calls of the function as possible. And it's basically because it's really hard to quantify algorithms if you include like every single thing you have to do, every single logic gate, because there's always like different circuits you can use. But by just counting the number of function calls or like oracle queries, it gives you a nice concrete thing that you can count to compare algorithms. And so classically, you need 2 queries. So you basically need to know both of the bits, and then you can compare the bits. Do they have even parity or do they have odd parity? So are they the same or are they different? And so if you only have one bit, there's no way you can figure out what the parity is, because depending on the other bit, it could completely flip what you thought the answer would be. So you just have to know both bits classically. So you need to do this in 2 queries. But with a quantum computer, with a quantum oracle, you can actually solve this problem using just 1 query. And so the last algorithm on the adder, that's just like directly converting a classical circuit to a quantum circuit, but there's no advantage to that. If anything, it made it more complicated, right? Because you had to use these reversible logic gates instead of your normal logic gates. This example is here because it's probably the simplest example where you do get a speed up. So in this case, you go from 2 queries to 1 query. And so let's see how this works. This is called Deutsch's algorithm. And in Deutsch's algorithm, we're going to start with a single qubit in the 0 state, and we're going to apply the Hadamard gate. So if you apply the excuse me, Hadamard gate to 0, what do you get? The plus state, which is 1 over root 2, 0, plus 1 over root 2, 1. And now we're going to query the oracle. The textbook talks about why the oracle looks the way it does. I'm not going to get into all that. It basically looks like this. So you get a phase of -1 to whatever the bit B0 is. And then over here, you get a -1 to whatever bit B1 is. So again, it shouldn't be like, oh, yeah, that makes sense. Like it shouldn't if you haven't seen this before. But there's a way to, you can show that this is correct for the quantum setting. And so, again, f of 0 is just B0. F of 1 is B1. So when you query the oracle, it does that. And now I'm going to copy it there. And we want to see what happens when they have even parity or when they have odd parity. So when they have even parity, if B0 is equal to B1, then these are both B0 now in the exponents there. So I can factor out -1 to the B0. So I have -1 to the B0 times the plus state. And if they have odd parity, then whatever, so if this one is B0, then this one must have the opposite parity. So one way to express that is as B0 plus 1, where you're adding mod 2, or you're adding in binary. So if B0 is 0, this is 1. But if B0 is 1, this is 1 plus 1, which is 2, but that wraps around to 0. So it's 0. So this ensures that they have opposite bits. And now I can factor out -1 to the B0, like that. So I have -1 to the B0 times the minus state. So you see, if they have even parity, you have some phase times the plus state. If you have odd parity, you have some phase times the minus state. Well, we can distinguish the plus and minus state just by applying, so this is what we just had, by applying the Hadamard gate again. And that will turn plus into 0 and minus into 1. So if you apply the Hadamard gate, this plus state becomes 0. This minus state becomes 1. And now if we measure the qubit, we'll either get 0. Well, if the parity is even, we're certain to get that the bit is 0 with probability 1. If the parity is odd, we're certain to get 1. So again, if the parity is odd, we'll get 1 with probability 1. And that allows us to distinguish what the parity is. So here, if the parity is even, we get 0. If the parity is 1, we get 1. And so we're able to determine what the parity is with only 1 query to the oracle, which is why it's faster. And something that's interesting is we found the parity without ever learning what the bits themselves are. So for example, if you got 0, you go, oh yeah, I know we have even parity, but you don't know if they're both 0 or if they're both 1. Similarly, if you get odd parity, you don't know if it's 0, 1 or 1, 0. And this is actually important because if you actually want to know both bits, you need 2 queries. But we don't need to know both bits. We just need to know their parity. That's only 1 bit of information. So we only need 1 oracle query. And so this is an example of a quantum algorithm that is faster than a classical algorithm. And that's everything that I prepared. So you can have some questions and discussion and about that. Anything? Yeah.
This might be a bridge too far, so you can not answer it.
Okay.
Say a student takes this class and that ends up being like most of what they see in quantum.
Yeah.
Can you connect it up to the workforce things that we were hearing about? Like what would a kid like this be prepared to contribute to? Like what kind of work, what kind of industries?
Yeah, I mean, this is obviously a great question for like Jake and many others who work on this. I think it depends on kind of what their other interests are. So for example, I had an economics major take my class. And so for them, like working in business where having some knowledge of quantum like could be very helpful. So if you want to work sales or accounting or whatever the business needs like that a quantum business might need, like you want people who know business but maybe know a bit about quantum, right? So that's an example. Same thing with someone in engineering, right? It was mentioned that a lot of the jobs are in engineering or in like and things like that. Like having a good engineer who's an engineering major but has some quantum awareness and some quantum understanding allows them to work in these quantum careers. If you want to go into quantum research, you probably still need to go to grad school at this point. But the idea is like they can apply to grad school expressing interest in quantum and be able to say like I took this course in quantum computing and stuff. Yeah, Brian?
I can kind of comment to that. Two things. One, there was a comment that was made during the folk section. Justin had mentioned this folk program, and I've worked with a couple of faculty members who were introducing quantum material in their courses, not necessarily a whole course like Tom's, but maybe just a few weeks. And there was a comment that, well, one of my students had, mentioned in their job interview or their application that they had some exposure to QIS, and even though it wasn't really a QIS specific job, that was kind of enough of a differentiator that they actually got their foot in the door and could get a job for that. So that alone is something that's valuable to students. We already see value for that. I think a course like this and other similar kind of introductory courses would probably prepare students for an internship at one of these quantum computing companies. I've had several students do that for my course, and they're not necessarily being hired to like develop quantum algorithms or something. They may just be code monkeys developing some interface stuff, but they have enough of that language that they can talk to people and again get their foot in the door. So I think there are a lot of like practical opportunities. This might not be the end point for their journey, but it might get their foot in the door for a lot of other things.
I think so. I'm a particle theorist, so I do a lot of quantum stuff, including quantum field theory and then causality and these things. But many of my students will not be staying in academia, unfortunately. So most of them will be working for the industry. I think it's probably we should reduce some of the things that they don't need for the industry. Time-dependent population theory. We spend a lot of time to teach these things. Probably instead, we should introduce some of these things as a part of the quantum class.
Yeah, I mentioned at the start that my students' feedback was that the classical computing chapter, which is like a third of the class, ends up being incredibly valuable for them because at least our physics students, like, they know how to do some Python programming, they know like some Mathematica, but they've never learned like how does a computer actually work, like anything about logic gates, things like that. And even some of our computer science students, the ones that take courses more along like software development or like app development, like a lot of times they don't see kind of stuff about logic gates and things like that. And so I've had really good feedback from them as well. And like you said, a lot of them are not going to stay in physics. And so, yeah, in some sense, preparing them with computational skills is more helpful for a broader number of jobs. Yeah, I think just over here.
So I want to go back to the technical thing. If I had 3 quantum bits, I would have to do 2 calls to the oracle. Is that right?
Yes.
And if I had 4, it'd just be 3 calls.
Yeah.
So the speed of the factor of 2 speed up happens just for the first.
Oh wait.
No,
No. Sorry, it's a half. So if you had 4, it would be 2. If you had, because you could just do parodies of pairs, right? Yeah. And if it's odd, then you have to round, right? Yeah. It's half. So it's a speed up of half.
You should have half as many calls to the oracle.
Yeah. Yeah.
I was thinking, with your comparison with reversible computing, it strikes me that's similar to surrogates. You don't have exact correspondence with quantum gates and classical gates, but you can kind of get a surrogate for each classical gate you point up. So I was thinking, it might be feasible to get, like if you have business majors, get an economic surrogate for quantum mechanics. Because like when you look at mathematical economics, since a lot of it is associated with classical mechanics, you can actually use mathematical economics as a surrogate for calculus, which I've done sometimes when I've taught calculus, and it helps students understand calculus a little better when they have a concrete thing they can associate with. So I was thinking maybe there's some kind of surrogate quantum computing with mathematical economics, because a lot of it is derived from physics.
Yeah, maybe. I don't know. Yeah, maybe something worth pointing out with the algorithms we just covered is, because you talked about going through reversible computing. So we had that big table. All right, this one. Like, in this case, all we're doing is replacing classical logic gates with other classical logic gates that happen to also be valid quantum gates. So there's not going to be any speed up here. If you want an improvement, you need to use quantum gates that don't exist classically. And so with the parity one, we use one of those. We use a Hadamard gate. Because classically, you can't have a superposition of 0 and 1. Like, this is something that you can only do quantum mechanically. And so this ends up being central to attempting to do something faster than a classical computer could. So when you develop quantum algorithms, it's not just translating a classical circuit into a quantum one. Although you can do that, and for simple problems, like, that's fine. But if you want to try to do something more cleverly, you have to use, again, quantum gates that are not classical gates. Yeah?
So I also want to recap, so you understand. I want to recap that because I just read your book over the last week. I proposed your book for my course because when I was here last time, and it sounded like something that would be doable. It's a great book, by the way.
Thank you.
Well, let's thank Tom again. That was an awesome introduction. Hopefully set us up for the rest of the workshop.